Hello. I welcome you all to this another interesting screencast. We are going to be solving this problem, and it reads: determine the outside surface area of the hopper. And the second problem reads: the hopper is filled to its top with core. Determine the volume of core if the voids, which are the air spaces, are 35% of the volume of the hopper. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Benam. Right. Of course, the problem is quite direct and quite simple, and especially for this type of regular shape, which is just a cylinder and a frustrum at the bottom. We know the formulas for the cylinder, right? So the surface area for the cylinder, okay, is equal to, we have the circumference on top there, 2 pi r times the height, right? So this is the formula for the surface area of a cylinder, right? For the frustrum, okay, if you know the formula for a chord, you could rewrite the frustrum as a cone and then subtract the top, or if you know directly, then you could write it as this: a frustrum, which is just equal to, given we have a frustrum like so, okay, so this is the top, number one, the bottom, number two. So say this is equal to half times the sum of the circumference of one side plus circumference of the other side, and then times the length, this length here, like so, the length of one side, okay, either length, in some books they say s. So if you know this, then you could work out the problem, but you should not forget to say this frustrum is closed at the bottom, so you also need that area at the bottom to include that surface area at the bottom. All right, so these are the formulas that you can use to calculate this directly without really going through these steps that I'm giving. But the reason why I'm solving this particular problem is coming from the very foundations of these formulas. Okay, formula for a cylinder, a formula for a sphere, a formula for any kind of object, right? For those objects that we are already familiar with, of course, we don't need to use this particular method, but it's user friendly for objects of irregular shapes. Okay, objects of irregular shapes. This method I feel comes in handy. This method was developed in 4th century by a person by the name of Pappus. Pappus of Alexandria. Okay, I'm sure this should be a city in Greece, right? In 4th century, Pappus developed this method for computing surface areas and volumes of any object. Okay, of any object. So it didn't matter what function defined the surface area. Okay, it didn't matter as long as it was an object governed by a function that is definable, then this formula applies. And then it was reinstated again. It was reinstated again in 16th century. In 16th century, the same formula by another person by the name of Giddens. Okay, Giddens. So this theorem, sometimes you hear it in books being called the theorem of Pappus and Giddens. Okay, theorem of Pappus and Giddens, which I feel is the foundation of probably there would have been work that was done earlier than them, but this was the foundation of the formulas for the surface area and volumes of any object defined by functions, whatever function that can define a body. Okay, right. So let's briefly talk about what this is before I start solving. So given you have an axis of rotation, and you have a function, I mean you have a curve can think of this as a curve being governed by a definable function. And let's say you cut a small area here, very small area. I mean a small length. Start with length. We cut a small length. Okay. And if you do so, and then at this particular point here, at the very point here, of course, this small portion of length will have its own radius. Let's imagine this has its own radius. Okay, it has its own radius. Okay, you can think of this radius as also just some centroidal location for this small area. Okay, so now if we were to rotate this small dl, right, to rotate it 360 degrees about this axis. This is our axis of rotation. This is the axis of rotation. Okay, if you are to rotate this, what do you get? You are going to get a very small area, right? A very small surface area. We're just interested in the surface area. So if you were to write this using calculus, then you would say this small area that we rotate round will give us such an expression, a small surface area. We are rotating it 360 degrees, or in radians 2 pi. So we are going to get a very small surface area we're calling dA is equal to 2 pi r. You remember 2 pi r? 2 pi r is the circumference, right? The circumference. So 2 pi r, and then now for us to make it an area, then we have to multiply by the length of this line, which we are calling dl. All right? Is it making sense? Great. So this is the small surface area of our dl, right? This is the small surface area of our dl. And if we are to integrate this on both sides, then we have area equal to, can factor out a 2 pi because it's a constant, then we'll remain with just r dl. And if you remember from our previous lessons of centroids and so on, you know that integral of r dl is also equal to just the centroid r bar times L. Remember this, right? Okay. This is equal to this, right? Remember this? And if this is the case, then we can write this as area is therefore equal to 2 pi r bar L. And let's say we have an object that is made using a number of lines. We can call it composite lines. Okay, then we can write this as surface area is equal to 2 pi, and then the summation of the product of all the r bars. Okay, so this is one part of the problem. I mean, this is how they resolved, or this is how they were determining this particular formula, purpose and giddiness. Okay, this is the foundation. So this is the formula we're going to be using for computing our surface area of any body. All right. So if the curve that defines it is not a regular one that we can just compute directly, then we'll need to have it integrated, right? But if it's a straight line, like in our case here, like look at this cylinder, we have this line here, we can apply it even here. So we have this line here. Okay, so if you are to get the surface area of this line, then you'll say we know the length of the line is 4, and EC centroid location from the axis of rotation is r, okay, which we are calling r bar. So if we are to place all these in our equations, then we'll have area is equal to, since we are rotating this 360 degrees about the axis of rotation, which is the z axis, we are going to have 2 pi, okay, r, all right, okay, and then times the length of the line, which is h. You've seen this. This is the formula for the surface area of a cylinder, right? Great. So we are seeing that this is really the foundation of these particular formulas. Okay. So this is for the surface area. Then let's look at the volume. Let me just wrap this quickly. Let's look at the volume. So instead of looking at, so imagine we have the same curve. Will not change. So instead of getting a small area of a small line, this time around we are going to get a small area, okay, a small strip. All right, a small strip of thickness dA, right? A thickness dA. So if we were to rotate this 360 degrees, which is 2 pi around the axis of rotation, then we can write this as, and when we do that, then we are going to get a very, very small volume we are calling dV. And this dV is going to be equal to 2 pi r. Again, remember, what is this? This is again the circumference, okay? Then times dA, okay? Then this gives us the volume, a very, very small volume. And if we integrated both sides, then we'll have volume is equal to 2 pi integral of r dA. And we know that integral of r dA is also equal to just r bar a, okay? And therefore now we know that therefore our volume can also be written as just 2 pi r bar area. And if it's made out of composite areas, then we can have V is equal to 2 pi summation of r bar area, like so, okay? So this would apply to anything, okay, any kind of a composite bottle with whatever type of areas that it is made out of. Therefore, generally the two formulas are written as surface area is equal to theta expressed in radians. So it must not necessarily be always 360 degrees. It can be whichever angle that you want to rotate, okay, your line, your small line, your line, or your area. It can be either 50 degrees, you convert it to radians, it can be whatever. So the general formula is just theta r bar L, okay. Maybe I write it for a composite. So this is the general formula, and volume we have theta summation r bar area. So these are the two general formulas that we are going to be using in solving the problems that we are going to start now from 9.9-92 and those that follow, okay. So when I talk about purpose and guidance, I would want you to refer to this particular video because I've done a brief explanation and background where all these theorems are coming from. All right. So having said so, let's solve this particular problem. I think I've spent a lot of time explaining the foundation of these particular theorems. So what we need to do now here, since we know the formula, what formula are we using? We are using area. Like I said, we can prove this using known formulas, but we want to use the foundational formulas. So we are saying surface area is equal to theta summation of r bar length, okay? And our theta in our case here is 2 pi, okay? Great. So we'll redraw this as just lines. We'll redraw this quickly. So we have the rotation, the axis of rotation, which is in red like this. Imagine this is our axis of rotation. I'll just draw one side of the line. So I'll have a line like so here. Let's imagine maybe up from there to here. This is one line. And then we have another line, the bend there, okay, like so. And then we have a small one. I've exaggerated this a little bit. Maybe I use another color for this. So let's say we have this like so, okay, then we have this like so, and then we have this like so, okay. So there we go. Let's number them. Let's call this one is number 1, and this one is line number 2, and this one is line number 3, okay. So we have 3 lines which is a composite. Body is made out of a number of lines, okay, composite lines. So now the first thing that we need to do is to define our error bars for each of the lines, right? So for line number 1, we know that is the error bar for this. We already know it is just error bar, error curled bar 1 is going to be equal to what? We've been told the radius of this cylinder is what? 1.5. And therefore, its centroid position for part number 1 is just 1.5 meters. And what about, let me also just try to dimension these parts so that we know where we're coming from. Great. Let me just dimension those parts so that we know where we are coming from. Thank you. All right, great. There we go. And then we also do the dimensioning at the bottom, like so. Sorry. Like so. And like so. Great. Okay. Where are we? Okay, there we go. So we are saying this part from there to there, this is 4 meters, and then up to there, this is 1.2 meters, and then from here to there, this is first we start there, this is 0.2 meters, and then since this is 1.5, therefore the difference here will be 1.3, right? Great. So we have these dimensions, we need them. So what will be the centroid location that's perpendicular to the line rotational to the rotational axis? It will be this point here. Mind you, we are looking at this direction from there to there, okay? So this one here, it is 0.65, right? So this is RKL2 is equal to, this one is equal to 0.2 plus 0.65, right? Okay. And then what about the last one but not the least, which is this one here, which is RKL3. What is this one? This one, of course, sorry, supposed to be to go halfway up to this point here, okay? Centroid location. What is this one? Of course, this one is RKL3 is equal to 0.1. Okay, is that fine? Great. So we have all the information for everything. We have all the information. So what we just need to do is quickly to draw. Before we draw a table, we need to define the lengths of the lines. So length, line 1 is length. What is this length? This length is 4 meters. What about line 2? Line 2, this length is root of 1.2 squared, 1.2 squared plus 1.3 squared. What does it give us? L2 therefore is going to be equal to root of 3.13, right? Is that so? 1.2 squared plus 1.3 squared. Yes, 3.2. And then therefore line 3, what is this length? This length for line 3 is 0.2 meters. Okay. So once we have this information, we can place them in the table quickly. We can draw a very small table with parts like we are doing in the previous case. So let's do that. Let's quickly do that. Great. So we have part. What else? We have arracled, and then this one is in meters. Then we have L, which is the length. and then find that we have the product, but we don't forget the angle. So multiply in advance 2 pi r cubed L, and this one is in square meters. Great. So let's finalize the table. I think I'll need to move these a little bit so that I have space. I just move them a little bit. Alright, something like that. So then let's fill in that particular table. There we go. There we go, something like that. Okay, so we have part ara, and finally that part. How many do we have? We have 1, 2, 3. This one is smaller. 3 and 4. Great. Okay, so I think we are done. The last is for summation. Let's fill in this table. So we have summation. We have part 1, 2, and 3. What is the arcade? The arcade is, the first one is 1.5 for the first part. The second part is 0.2 plus 0.65 is 0.85. Then the last one, but not the least, is 0.1. What's the length? The first one is 4. The second one is root of 3.1. Why am I writing like this? To just preserve the accuracy. You don't have to do that. Then the second one is 0.2. Then we have the products. Let's get the products. When we do the multiplication, that's 1.25 by 4 by 2 pi. We have a 12 pi. So we are using this one here on top. Okay, r by L by 2 pi. Then we do the multiplication for the second one. We are going to have 1.7 root of 3.1, just 1.7 pi by root of 3.13. Great. And then this other one is a 0.04 pi. When we sum these, when you do a summation of all these, you get, let's do a summation. We have 12 plus 1.7 root of 3.13 plus 0.04 times pi. So we have a 42.27. Okay, 42.27. Therefore, the surface area, so the surface area includes, the bottom is closed. Okay, the bottom is closed. That's the reason why it's closed there. So it's closed. The only part that is open is on top. So the surface area, therefore, the surface area of the hopper, the surface area of the hopper is equal to 42.27 square meters. Okay, but we are not yet done. We just found the surface area. We need to find the volume. Okay, we need to find the volume. All right, so what we are going to do is we're going to use the same figure. We'll use the same figure. The only thing that we're just going to do is just drawing another table. So let's use the same figure. So I'll just rub this stuff here. I'll just rub this and then just clear this part. I'll need to clear a few things. Sorry about that. I'll use the same table. The lengths will remain the way they are. I'm just clearing the inside, okay, because these are the only things that will change. We are dealing with now the area. Okay, there we go. And I think maybe this I'll be writing them inside the figure. Okay, great. There we go. So we have this part here closed up. Okay, so let's define our areas. So I'll make this as my first area. Okay, and then which other area will I make as again, it's up to you how you define your areas. Okay, this is not standard. So I have my first area, I have my second area, I have my third area. Okay, these are areas. Okay, so once I've found the areas, I'll need to find their centroidal location, and this centroidal location is perpendicular to the axis of rotation. That is very vital. All right. So now what is the for the R? So the formula we're using for this is V equal to theta summation of R curled by area, where theta is equal to 2 pi. Okay. So what is the position for this? This one is a rectangle, so it will just be at the midspan. Mind you, the length of this radius is what? Is 1.5. So this will be is R at this point from the rotation. So is R curled 1 will just be half of 1.5, which is 0.75 meters. Okay. What about the triangle? The triangle, you are measuring from there to there. What is that length there? This is always what? This is one third of this length, one third of 1.3. Okay, is it clear, that one? Let me use a small font. This is 1/3 of the length of that triangle, which is 1.3. Remember the way we're getting centroids. So if I have that, therefore starting from my point of my axis of rotation, because that is always my reference, I'll move up to there like that, up to there. Therefore my R2 curled is going to be equal to 0.2. Okay, 0.2 plus 1/3 of 1.3. Okay, is that okay? Great. And then what about this one here? It is just a center of this one is just R curled 3 is equal to half of this. This is a 0.2, therefore 0.1 meters. So we have all the information. What is the next step? We just need to find the areas. What's the area for the first one? Area 1. What's the area for the first one? Is 1.5 by 1.5 by 4. What does this give us? It gives us a 6 square meters. Area 2, what do we have? Is a half a half by 1.2 by 1.3. What do we get? What do we get when we do the multiplication? We get a 0.78. Area 3, what do we have? It is just a 0.2 by 0.2 by 1.2. What do we have? What do we have when we do the multiplication? What do you get when we do the multiplication? You are going to get a 0.24. Great. So we have all the information. We just need to fit them in a table. Let's draw a table again. So we have part. We have R curled in meters. We have, instead of L, we'll have area. And then we'll have 2 pi R area, and is in cubic meters. This is volume. So let's draw quickly. We draw a table like we did in the other case. We draw a table, something like that. Okay, there we go. There we go. Great. Okay, we have how many rows? We just have 3 rows. One, the fourth one is for summation 2 and 3. This one looks a little bit slim, right? And the fourth one, great. We are almost there. Let's hold on a little bit. I may have taken a little bit of time because of the introduction. Sorry about that. My apologies. So the parts, let's number the parts. We have 1, 2, 3 and summation. And what are these? Let's fill in the centroid locations for area. First one is 0.75. Second one is 0.2 plus 1/3 of 0.2 plus 1/3 of 1.3 is what? This is 0.6333. Okay. What's the third one? The third one is just 0.1. The areas, we have 6 there square meters. The other one is 0.78 and third one is 0.24. Okay, let's work out the products. What we have 9 pi there. The second one we have a 0.987948. I didn't want to round off this. 987948, and then the other one was 0.048 pi. When we sum up everything else and we round off the answer, we'll have a 31.53. This is the total volume. So we'll say volume of the hopper is equal to 31.53 cubic meters. Okay, so this is the volume, but we've been told that part of that volume is being occupied by voids. Okay, 35%. So we have been asked to find the volume of the core. So we need to subtract 35% from the 100% volume. So what we do? So 100 minus 35 is 65%. Okay, or in decimals it is 0.65, right? So we need to multiply 0.65 by 31.53 to find the volume of the core. So we'll say volume, therefore volume of the core in the hopper, okay, is equal to 31.53 times 0.65. You know where it is coming from? That is 65% that remains, which is equal to, so when we do the multiplication, 31.53 by 53 by 0.65, we get a 20.49. So a 20.49. Okay, so cubic meters. So that is the final solution. Let me just move it a little bit this side. So that is the final solution for this particular problem. So we found the volume of the core in the hopper, which excludes the voids. We've also found the surface area of the hopper. You can confirm these particular answers that we found using the regular defined or developed formulas. You find they are really going to match. Alright, I think this is about it, and I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and sharing my channel. Bye bye. and see you in my next screencast.